We click, we tap, we type, and websites just appear. It feels like magic, right? But it's not. Behind every single click is this hidden, high-speed symphony of technologies. So today, we're going to pull back the curtain and look at the internet's invisible engine.
Seriously, think about that for a second. That one simple action, it kicks off this incredible globe-spanning journey for a tiny packet of data. We're going to follow that journey step by step, from the moment you hit enter to the second that content pops up on your screen.
Okay, first things first. Before your request can go anywhere, it needs to know where it's going. I mean, it's just like sending a letter. You can't just write a name on it, you need a specific street address. And for the internet, finding that address is the job of DNS.
And that phone book analogy, it is absolutely perfect. See, we remember names, right? Things like example.com. But computers, they only understand numbers, these long, complicated IP addresses. DNS is that critical translator that looks up the name you type and finds the number your computer actually needs to connect.
Now, this whole lookup happens in a flash. Your browser first asks something called a resolver for the IP address. And this resolver, it goes on this little scavenger hunt. It asks a main root server, which then points it to the right server for the domain type, like .com. That server then points to the final, authoritative server that has the specific IP address. The answer gets sent all the way back, and this all happens in a fraction of a second. It's wild.
And that, right there, is why DNS is so critical. It makes the web usable for us humans. Can you imagine trying to memorize dozens of these long IP addresses? No way! You just wouldn't do it. DNS handles all that complexity for us, turning the numerical internet into a world of familiar names we can actually use. So our request has the right IP address. We know our destination. Awesome. But the internet is this massive, sprawling network of networks. How in the world do we find the best path to get there? Well, that's the job of the Internet's Postal Service, BGP.
Think of BGP as constantly looking at a live map of the entire internet. This map is made up of thousands of huge individual networks called autonomous systems, or ASs. You can kind of think of them like regional postal districts. And just like a postal service finds the best route for a package between districts, BGP finds the most efficient path for your data to hop across all these different networks to get to where it's going.
So BGP actually works at two different levels. You've got internal BGP, or iBGP. That's kind of like the local mail carriers sorting letters inside one post office. But then you have external BGP, eBGP. That's the long-haul truck that carries the mail between all the different cities. It's what actually connects all these individual networks to create the global internet we know and love. But here's the catch. BGP is built on trust. Networks basically just trust the routes that their neighbors announce. And as you can see from these examples, that trust can be broken, either by accident or on purpose. A bad route announcement can spread like wildfire, redirecting huge chunks of internet traffic to the wrong place, causing massive outages or even enabling theft.
The good news is there's a fix being rolled out called RPKI. Think of it like a digital certificate of ownership for IP addresses. It uses cryptography to prove that a network is actually allowed to announce a route for its addresses, which helps stop these fake announcements cold. It's a huge step forward for security, but it only really works if networks everywhere get on board and adopt it.
All right, we're almost there. Our request has the right address, and it's taken the fastest route. It has now arrived at the destination server. So, what happens next? Now the actual conversation to request and receive the web page content can begin. And these days, that conversation is happening in a new, much faster language, HTTP/3.
For decades, HTTP/1.1 was the foundation of the web. Then HTTP/2 came along and made things a bit faster. But both of them were built on the same old infrastructure. HTTP/3 is a whole different beast. It's a fundamental shift, a complete rethink of how browsers and servers talk, and it was designed specifically for the modern mobile internet.
So the biggest change by far is the move from a protocol called TCP to a new one called QUIC. Now TCP is super reliable, but it can be slow. If one tiny piece of data gets lost on its way to you, everything else has to stop and wait for it. It's a real bottleneck. But QUIC is way smarter. It sends data in multiple independent streams. So if one stream hits a snag, the others just keep on going. This makes a huge difference in speed.
And this is where that change really pays off. As this chart from the source research shows, when network conditions get tough, like when you're on a spotty mobile connection with a lot of lag, HTTP/3 just pulls ahead. It shaves valuable time off the page load, creating a faster experience right when you need it most.
The researchers really nailed it here. HTTP/3 isn't just about being faster for the sake of being faster. It's a targeted solution, one that's designed to fix the specific slowdowns we all feel on our modern, sometimes unreliable mobile networks.
So who's pushing this change forward? Well, it's the internet giants. We're talking Google, Facebook, and Cloudflare. At their massive scale, even tiny little performance gains have a huge impact. So naturally, they were the first to adopt HTTP/3, and they're the ones driving its rollout across the web.
What the research also found is that website design really matters. It turns out HTTP/3 works best on pages that are built efficiently. Pages that don't have to fetch content from dozens of different servers. As more developers optimize their sites for this new protocol, the speed benefits we're seeing should get even better.
So, we've seen the three key players in this story. But the real magic isn't in any one of these protocols. It's in how they all work together, this perfectly coordinated, high-speed symphony that plays out every single time you go online.
So let's just recap real quick. First, DNS acts as the phone book, finding the right address. Then, BGP acts as the postal service, charting the most efficient course to get to that address. And finally, HTTP/3 handles the actual conversation, delivering the web page's content using a faster, more modern language. This whole intricate dance, find the address, chart the route, deliver the content, it happens in the blink of an eye, billions and billions of times a day all over the world. It's the invisible, unsung engine that powers our entire digital lives, and most of the time, we don't even know it's there.
From HTTP/1.1 all the way to HTTP/3, these systems are constantly evolving to meet new demands. It really makes you wonder, what new challenges will the Internet of Tomorrow face, and what new invisible engines will be invented to solve them? Thanks for watching.